I believe that was the homework, right? Anyone? Guys, can you hear me? It's like a radio silence. No, this was for chapter 17, the one which we are doing, advanced topics in equilibrium. So we were discussing about the problem that you see right now in front of you. And I mentioned in this problem. So we found the pH before adding HCl. Now we wanted to find pH after adding HCl, and we wanted to see the change in pH, right? So this was about the buffer solution, and I specifically mentioned that there was a problem with the equation, and I did mention over here what was the problem. And then we went here, we started to correct it. There was still a problem here. And then we got to that point. And I mentioned there was a problem over here as well. Now, how do we solve something like this? Did you guys go through this before? I mean, as a homework? You can just write yes or no on the chat box so I know. No, I'm not talking about finding another problem. I'm asking about solving this problem. I'm asking about solving this problem. So I still just got 2 responses. I want response from everyone.
I completely forgot.
Okay, so just send me the response on my private chat. You don't have to put it in the group chat. That's okay. Okay. So here's what I'm going to do. I will use the same problem. I'm going to move this slide. I'm just going to copy this slide and I'm going to put it here. And I'm going to solve it one more time for you guys. That way, let's see if it lets me copy that. Okay, so I'm copying it one more time. Yes, I mentioned that before leaving. I mentioned that. I absolutely remember what I say in the class. That's why I mentioned this question marks over here. So this was supposed to be the homework, guys. So if you are here, you would know that. If you're not, you would not know that. Simple as that. Simple and straight, right? So here's the thing. So first we found the pH of this solution. How did we find? We simply put the values for the salt, acetate salt, and the undissociated acid concentration in Henderson's equation. That's what you see on your slide, right? And you found the pH equals to pKa plus log A over HA. And you put those values and you found those things, right? Okay, that makes perfect sense. But now we have added 0.350 moles of HCl. So first you need to convert this into molarity, and which you guys already did that. So I'll just show you what you did here. You converted this into molarity, and this was supposed to be the value, 0.07. That was supposed to be the value. Okay, so I'm going to show you 2 ways to solve this one, and we'll be seeing the same result. And for this particular problem, we will be doing a virtual lab, right? So I'm going to share that lab with you, and you will see whether we get the same numbers that we see in the calculations, whether our assumptions are correct or not, right? So it's going to be quite interesting. So I'm going to write down that equation one more time for you guys. So we had acetic acid. It dissociates into acetate ions plus hydronium ions, right? Okay. Now, in this case, you are given a buffer solution. And this buffer, which you just found, the concentration that was zero point 0.1 molar in acetic acid and 0.1 molar in acetate. So I'm going to write down the same thing. So this is 0.1 molar in acetic acid, 0.1 molar in acetate. So far, so good. All of you agree with me so far on this?
No. Isn't there a minus sign in the initial on the reactant?
And why would there be a minus sign on the
Because
reactant?
being consumed.
That's for the C portion, not the amount.
Very good.
That's for
Very
the
good.
C in ice.
Very good, Kimberly. Very good. So basically, this is the one which I gave you. I gave you the mixture right away. Before it undergoes ionization, before acetic acid dissociates, I'm giving you the mixture of acetic acid and acetate ions. I'm giving you that mixture already. It's an equal amount. I'm already giving you that, right? So before acetic acid dissociates, this is what you get. All of you agree with this so far? Let's see. Because in this case, you will have to stay with me every step because you never know where these problems will show up. And these are quite intricate problems. You need to have a very good understanding when what is going on. So let me draw this one for you. So you are given equal amount of acetic acid. So yellow is your acetic acid and green is the acetate ion. This is what you are given, equal amount, right? Okay. Now, when you put it in water, what would you expect to happen with acetic acid? Do not worry about what happens to acetate ions at this moment, but tell me what will happen with acetic acid. Because you were given undissociated acetic acid and acetate ions, and now you are putting that mixture in water. Can you tell me what would you expect in that sense? What would you expect to happen in that case? You are putting that in water now. You put this whole thing, you just put this whole thing in water. What would you expect in terms of hydronium ion? Will dissociate actually? Yes, absolutely. So suppose acetic acid dissociates X amount of acetic acid dissociates into acetate ions and hydronium ion. Can you tell me how would this look like in terms of equilibrium? What would be the change that you are expecting? Negative X. Okay. So when you say negative X, that means 0.1 molar negative X, or how should I write it? Negative. Okay, negative acetic acid concentration. So I'm just going to write it here. Negative acetic acid concentration, that's the change. So some of the acetic acid is removed. And then what should I see on the right side? Positive X, that's right, Gil. Very good. So I'm going to write here positive X. And this is also positive X because it's the same amount. So acetic acid will dissociate into equal amount of acetate and hydronium ion. But now the thing is that you already have acetate ions that you were given in the starting. So how much acetate ions should I have at equilibrium? acetate ions. Okay, so I can see one answer already there. Guys, can you just pitch in? I would need response from all of you because I want all of you to solve this problem. This should have been done in your homework. Okay, so acetate ion concentration, I can see you have written 0.1 plus X. Hydronium ion stays as X. And what should be acetic acid, undissociated acetic acid concentration? Good. So I'll just write the way you have done it. So 0.1 minus X. Now, in this case, you can use exactly the same values at equilibrium. Now I'm going to put it here at equilibrium. So I'm going to put it in box. This is the equilibrium that is already existing in your buffer solution. You put this mixture in water and this is what you get. It's already there. Now it's at equilibrium, right? And this equilibrium is given by Ka. That would be the concentration of acetate ions. So I'm going to put it here, 0.1 plus X, hydronium ion X divided by 0.1 minus X. That's going to be your acetic acid final concentration at equilibrium. Now, you know the value of Ka, so this turns into a quadratic equation, right? Now, either you can use the quadratic equation to solve this problem, or you simply use these values the way we did it using Henderson's equation. Now, for Henderson's equation, it's quite simple because we just have the two components. So this equation will reduce down to the Henderson's equation anyways. So you don't have to worry about it, right? So this whole equation will end up into Henderson's equation. Okay. Now, what happens if this equilibrium is disturbed? If I add HCl to this equilibrium. Now, before I do that, I will copy the whole equation one more time onto the next slide. Now, this equilibrium is already existing. Now I'm adding hydronium ion from outside. Can you tell me what would happen if I'm adding hydronium ion from outside? Before you answer that question, let me draw the diagram that I had earlier. This is what you had at equilibrium, right? You had, if I say the right side is acetate ions, and the left side is undissociated acid, and it appears to be equal, but then it is not equal because look at the equilibrium. Your acetic acid concentration is 0.1 minus X, but then X is too small, so we are not going to think about it. That's going to make a big difference, right? And then this one is slightly higher, very, very slightly higher, 0.1 plus X. Okay, this was supposed to be what I had. Now I'm adding, keep in mind, I'm adding hydrochloric acid, right? I'm adding hydrochloric acid from outside into this solution. Now, can you tell me with which species will hydrochloric acid react with? When I say hydrochloric acid, you are looking at H plus ions. I'm adding H plus ions from outside, or let me make it a little bit more clear, hydronium ion. This is what I'm adding from outside. Absolutely. So if I add hydronium ion from outside, where should my equilibrium shift to? Should it shift to the left side, the one that you see on the previous slide, or should it shift on the right side? Le Chatelier's principle. To the left side, absolutely. So I will be moving towards the left side. Okay. Now, when I do that, can you tell me what should be the concentration of acetate ions when the whole thing shifts to the right side, left side? So first I will show you in terms of concept, and then we will do some equations on it. Okay. Let's see what we have. So now since you said in the chat, I can see that acetate ions are the ones which are going to react. So their concentration should fall down. All of you agree with that? No. Okay, so be careful when you say negative X, because X is the amount of acetate ion and hydronium ion coming from the dissociation of undissociated acetic acid, not from hydronium ion. So yes, that amount is going to be affected. So this whole amount is going to be affected. This whole amount is going to be affected, but in a different way. Now I'm going to see more of acid and less of acetate ion. Now I've just exaggerated in the diagram so you can see it, but then it's a tiny change just to let you know. This is my acetate ion, which is left over, and this is my undissociated acid. Now that concentration has increased. Now, suppose if I'm adding 0.07 molar, this is what you added, right? Because you remember you did the calculations. You did the calculations. This was the amount that you added. Let me go back, right? So you added 0.35 moles of HCl, and this was in 5 liters. So that amounts to 0.07 moles. Molar solution. That's what you had. Let's go back to this thing. Now, when I add this amount, can you tell me what should happen to this number? Because I already gave you how much acid I'm using. Very good, Roberto. Very good. So this amount is 0.1 plus X minus 0.07. What can I say about this amount? Awesome. Very good, Roberto. So this amount initially was 0.1 minus X. Now it's going to increase, right? Because you're making it. So 0.1 minus X plus 0.07. Well. This is what we have at equilibrium. Now, I got the concentration of my undissociated acid. I got the concentration of my undissociated, my acetate ions in the solution. Now I can do two ways, right? Either I can use Henderson's equation. So I'm going to show you the first way, and then I'm going to use this equilibrium as my initial equilibrium, and I'm going to disturb it by adding 0.07 molar HCl. So I'm going to show you two ways. So Henderson's equation, quite simple, pH equals to pKa plus log salt concentration divided by undissociated acid concentration. Okay, this one is 4.74. We know that because of acetic acid has Ka of 1.75, 10 to the power negative 5. So this one should be 4.74 if you take a negative log of it. Okay, and now I'm going to take the log of acetate ion concentration. And what is that? That's going to be 0.1 plus X minus 0.0. This is divided by 0.1 minus x. Now, guys, keep in mind, this is the whole log. It's not that you have taken the log on the top and then you are trying to divide the bottom by HA. This is the whole log, just to make the things clear. You should know about that. Now here, we are going to take an assumption. What would be that assumption? The amount of X is too small compared to 0.1 and 0.07. So we are going to ignore. Okay, not to use that one. So I'm going to ignore X in both the situations, right? Why I can do that? Because X is too small because you are dealing with a weak acid. Weaker the acid, smaller the X is, right? Okay. Now, if I do that, I get to the point 4.74 plus log 0.1 minus 0.07 divided by 0.1 plus 0.07. Can you do the math for me? Anyone so far with the math? Okay, so that's right. So we are getting 3.99. Was it, let me check, was it 4.74?
I
Oh, no.
got 3.99 as well.
Yeah, actually, this should be 4.78. So can you do it again? Because this one is 1.75, 10 to the power negative 5 is 4.78. That's what we calculated. So we will stick to that one. That's right, Roberto. So I will change it a little bit here. So 4.78. I'll change this one, 4.78. And this one is 4.03. Good. So all of you should be getting 4.03 pH. Now, in terms of observation, you are adding acid into the buffer solution and your pH went from 4.78. So I'll just write here, it went from 4.78 to 4.03. That was not a big difference. It was a very, very tiny change, right? Believe me, if you had added the same acid to the neutral solution, the pH would have been it would have been roughly 0.03. 0.03. It would have been that acidic, right? But then here, the change is so small. I mean, it's in that comparison, I'm saying, right? If you add the same acid to the neutral solution, you're going to see a big change. Whereas in case of buffer solution, it goes from 4.78 to 4.03. Now, let me show you the second method. I'm going to copy this whole thing one more time so that you should know both of them. Okay, now this was the equilibrium that we started with, right? This is the equilibrium that we started with. Now, if I add hydronium ion into this, what should happen? So I will make this as my initial concentration. So this becomes my initial now. Like I'll just write down acetic acid plus water at equilibrium gives you acetate ion and hydronium ion. And you had 0.1 minus X, that was at equilibrium. This was 0.1 plus X at equilibrium. You have X at equilibrium. Now, if this becomes my initial change and equilibrium. Now, in this case, I am adding hydronium ion from outside. What should I write in terms of change? If I'm using this as my equilibrium, be very careful when you answer this question. See, it was quite simple to see here in the concept. Now I'm trying to put it right here. Now I'm adding hydronium ion from outside. Where is the equilibrium shift? Okay, let me see. Plus 0.05 of acetic acid, negative, isn't it? HCl. Yes, that's HCl. So basically, when we think about HCl, we are not looking at we are not looking at a spectator ion, which is Cl minus. We are just looking at hydronium ion. So I'm adding hydronium ion from outside. That means I'm adding this one. Now, guys, just keep in mind, the moment I add hydronium ion, what should happen? What is the change? Keep in mind, you will have two equilibriums over here. Finally, your equation is going to look like this one, exactly like this figure. Okay, so you are right, 0.07 H plus. Okay, so if I write 0.07 H plus, that means I'm adding H plus. Okay, so I will just write down as you are saying. And be careful, this is the point where last time you guys went into the wrong direction. So I just want you to focus on this one. So when I'm adding excess amount of hydronium ion, 0.07 from outside, you will be tempted to write 0.07. Okay, now what? If you do that, what happens next? It will react. Very good. Then what should happen? If it reacts, then what happens? That's right. So we got a problem with the sign. See? So this sign is a problem because what you're not seeing is another equilibrium which is now driving to the left side. So this sign should be negative. I agree with you guys on that one, right? I will give you that. Very good. So if this is negative, so this 1.1 plus X is going to take out exactly the same amount on the left side. So this becomes 0.07. Am I right on that? So right now I'm just writing it on here. So this one, 0.07, and this one plus 0.07. Now, did you notice something here? Despite you added hydronium ion here, we put the negative sign. And now you know where this negative sign is coming from. Because when you increase the concentration of hydronium ion, you are shifting the equilibrium to the left. You are generating undissociated acid. So I'm just responding to the comment on the chat. So let's see what we have here. Well. So what do we get on here? What should I write here? Because guys, keep in mind, if I put that one as 0, we will have a big problem. I will show you what is that. Ka, that's going to be equal to acetate ion concentration multiplied by hydronium ion concentration divided by undissociated acid. If I plug in the value for this one over here, if I plug in the value for this one over here in my Ka equation, everything looks okay. But now if I put it as 0, the whole Ka term will be equals to 0 because anything multiplied by 0 will be 0. So whatever you have here is going to be very, very important. What is that? Very good. Very good, Roberto. Very good. So when you move the equilibrium to the left side on acetic acid side, the ratio between acetic acid and hydronium ion at equilibrium is the same as that you had it over here. So this one should turn out to be X. Well, we got all our ingredients ready to go in the Ka equation. So let's put it in the Ka equation. So Ka equals to acetate ion concentration, because Abram, if it becomes 0, your Ka becomes equals to 0. And it never becomes equals to 0 because there is an equilibrium, right? You can shift the equilibrium to the left side, but eventually the ratio will be maintained, right? So the ratio between acetic acid and hydronium ion will be maintained. So that ratio is X. Yes. So X is negligible. That is right. But then negligible compared to what? So you can remove X when you are thinking of adding and subtracting X from a big number. But then if there is no addition and subtraction, you cannot simply ignore it. So I'm just answering a question on the chat. Okay, so now I'm going to put those values 0.1 plus X minus 0.07. This is my acetate ion concentration. Hydronium ion concentration is X. When I go down, that's going to be 0.1 minus X plus 0.07. Now, Abram, this is where I'm going to make that assumption, the way I did it earlier, right? Now, what is that assumption? I can simply take out X as my, I can simply take out X as a small number compared to the rest of them, right? So take out X, and what do you get? Point 0.03 multiplied by X divided by 0.17. And Ka is 1.75 10 to the power negative 5. So your X would be equals to 1.75 10 to the power negative 5 multiplied by 0.17 divided by 0.03. Can you calculate that for me, guys? And tell me what you're getting. Any answer so far on this?
I got 9.92 times 10 to the negative fifth.
9.92, 10 to the power negative 6. That looks correct to me. That
Sorry,
looks,
5.
that's fine.
Negative
Okay.
5.
Negative 5. Okay. Now, when you are looking at this x, what exactly is x? Look at the ICE table. X is your amount of hydronium ion in the solution. Well, if we have that, x equals to the hydronium ion concentration. So if I want to find pH, I can simply take a negative log of 9.92, 10 to the power negative 5. Can you find this value for me? Well, 4.00.
4.0.
Okay, very good. 4.00. This is what you guys are getting. See, now we use two methods to get to the same answer. Now, you would wonder, oh, we have been making assumptions all over the place, right? We assumed here, then we've assumed here. I mean, we did a lot of assumption. So what is the proof that this is going to be exactly like that? Well. I'm going to show you one simulation, and we are going to do a lab experiment, a virtual experiment using the similar situation, right? The same experiment, and then we will see whether we are getting our pH closer to 4, right? Okay, so give me a second, guys. Yeah, this one is quite a good simulation, I can tell you that. It's quite cool. If you guys want, you can also do it back home. It's good, quite a good one. Okay, let me see if I got everything here. Okay, so I'm going to share my workbench with you. This is, tell me if you guys have seen this before. Have you guys seen this before? Guys, can you see
I
me?
have not.
No, you
No.
have not seen that, right?
No,
Okay.
Professor.
Okay, no, that's fine. So here we are going to take 1 molar acetic acid. We got that. We also need, we'll go to the stock room. We need the conjugate base. Where is acetate ions? No, conjugate. Let me see, where can I find it? Should be here. Okay, I got acetate ions. But see, I got 1 molar. We don't want 1 molar because we have been using 0.1 molar, right? Okay. And let's go to the stock room. What else do we need from here? We need volumetric cylinders, volumetric flask, not cylinders. I go to the stock room. I get the volumetric flask. I got a first one. Okay. And we also need water because we are going to dilute it, right? So we are going to use that one. Let me see. Where is water? Oh, we got a lot of distilled water. Okay. So, guys, right now we have 100 milliliter volumetric flask, right? And I want to make a mixture of acetic acid and sodium acetate, which is your acetate salt, which should be 0.1 molar. How much acetic acid should I add in this volumetric flask, in 100 ml volumetric flask? Now here, you will be using the same formula, M1V1 equals to M2V2. Okay, you know the you know the concentration of acetic acid in this flask. You already know that. You know how much you want to have it. So I know that I want to prepare 0.1 molar solution. And I know that it should be 100 ml. The total volume should be 100. Do I know the molarity of my starting solution, stock solution? So this one is stock solution. It's 1 molar. How much volume should I take? So my V2 turns out to be 10 ml. Well, I'll take 10 ml and I'm going to put it there. I'm going to pour it, put it back here. So this is what we have at, let me clear up this thing. Okay. So now I have 0.1 molar in acetic acid. I'm going to add the same amount because the same thing. And now when I dilute it to 100 ml. Oh, what just happened? Why
You
is
got a
one of
10 extra ml of water.
no, it's not 10. I added 3.3 more. Why it added 3.3 more? It should have gone to, I should have, okay, let me
Professor,
see.
you had 20 ml on the thing and you added 90. I don't know why
Yeah,
it shows 103, but
you saw that, right? I added 80 and okay, let me do it one more time because no. I'll take volumetric flask one more time, 100 ml, take it, oh, take it here. I add 10, pour it, leave it, okay. Then I add acetate ion, add 10, pour it, leave it. So I got 20 ml over here. All of you can see that. Now I need to add 80 ml. I'm adding 80. Well, this is good. Now this is fine. See this one, do you see the pH of this solution on the left side? This is exactly, I mean, not exactly, it's very close to what we found, 4.78, right? So 0.1 molar acetic acid mixed with 0.1 molar sodium acetate. The solution that you get is having the pH of 4.76. All of you agree with that? Do you see this one? Do we have any doubts so far on this?
no.
Okay. Now I'm going to make another solution, guys. I need a strong acid. Well, I'm going to take HCl. I'm going to leave HCl here. This is in my stock solution. Okay. And I'm going to prepare another solution. So you can compare what we have already and you can compare it with the previous one. Okay. So this is the solution that we already made. So this is the solution that we already made. And this is the pH of that solution. Okay. Now, ideally, I should be adding HCl into the buffer, but I'm not going to do that because I need to compare both of them so you can see side by side. Now, again, I'm going to prepare a buffer, putting 10 ml in this acetic acid. I'm going to put 10 ml of acetate ions. Okay, now I need to add 0.07 molar solution so that this solution, HCl solution in this flask is 0.07 before it reacts with the buffer. So what I'm going to do, the same formula, M1V1 equals to M2V2. Okay, do we know the final concentration of acid that we want? in this flask? Answer is yes. Do we know the volume of this flask? Yes. Do we know the initial concentration of our stock solution? Yes. Do we know how much volume we should be taking? Answer is no. If you find this one, can you tell me the answer? What should be the V2? How much I should be adding into this one?
Uh, 2.33 repeating.
Is
So
it
7/3.
okay? So 7/3, that means around 2.3. That's what you're saying?
Yes, Professor.
Okay, so 2.3 mils I should be adding into that. Okay, I will just add 2.3 mils. And now I should be filling up this whole thing with water. So I have already added 22.3 milliliters. How much water should I be adding into this to make the volume 100 milliliters?
$77.7.
77.7. Well. We got our volume to 100. Look at the pH, guys. Do you see the pH? It is quite close to what you guys found, 4.02. Does it make sense? Did you see that? Now let me show you. What would happen if I add acid directly into water? The same amount of acid, not different, the same amount of acid. If I add into water, let's see what happens then, right? So the first one is pure buffer. The second one is when I added 2.3 milliliters of this solution into buffer. Now I'm going to put the same amount of acid in the neutral solution. I mean, in the neutral water. Let's see what happens in that case. Guys, can you tell me how much water should I be adding? Because right now I have 2.3 milliliters in this. How much water should I be adding so that the total volume is 100 milliliters?
$97.7.
97.7. Okay, I added 97.7. Guys, look at the pH. It went to 1.16. The same amount I added in neutral water, the pH drop was from 7 to 1.16. You can see the big difference amount. See, I added the same amount in here, 2.3 milliliters, which is 0.07 molar. I added the same amount over here and look at the pH. So the here pH went from 4.78 to 4.02. Here pH went from 7.00 to 1.16. Look at the drastic change. That's why we call this as a buffer solution. Does it make sense, guys? All of you on the same page?
Professor, could we like go over like the math, what it would be like for like just water, like adding 2.3? Like
Oh, absolutely. Yeah, absolutely.
how it turns
So
out to be one.
no. It's a good question. Let's do that. So when you added 2.3 milliliters into that, what was the concentration in this one? So this one was M1V1 equals to M2V2, right? So if I just find the concentration, just think in that way. I don't know what was the concentration in this one, so I'll just write it here M1. But I know the final volume is V1. And I know how much I took, so 2.3, but I also know the concentration in that way. So 3 multiplied by 2.3, right? So M1, if you do the math, it will turn out to be 0.07. This is the molarity, right? But since this is a strong acid, everything that you see as HCl has dissociated into hydronium ion and Cl minus ion. So when I say 0.07 molar HCl, I am saying 0.07 molar hydronium ion. And what would be the pH? pH equals to negative log. Can you find it for me? Negative log of 0.07. Can you find pH for me? Good. So it's roughly 1.15, right? That's what you're getting?
Yeah, that's what I got.
Exactly. So this would be the math which would be involved when you are adding HCl into the neutral water. Make sense, all of you? Guys, are you there? Or am I the only one?
Yes, Professor.
Okay. Now, see, the good thing about the buffer is it can withstand the change in acid concentration as well as base concentration. So we just saw about the acid concentration. We added acid and there was no change. I mean, there was a change, but not to that much, right? What would happen if I add base into this? Yes, the pH is going to increase. Just like when you added acid, the pH did decrease, but not to that extent. If you add base, the pH will increase. The calculation stays the same as we did for acid concentration, exactly the same. But I'm going to show you in this simulation how that one looks like. So I'm just going to remove this one because we don't need this. We don't need acid anymore. I need to remove this. That's gone. We don't need this one. I'll just keep it there. I'll just keep this one above here. This is our stock solution, the buffer solution that we prepared. Now, I'm going to prepare another solution. I'll take a volumetric flask, put it there. And this time I'm going to add strong base and see what is the change, right? And I'm going to add sodium hydroxide. Let's say I have 1 molar sodium hydroxide, which is right here. Oh, this should be here. Okay, I'm just trying to organize my bench. Okay, I'm going to use the same buffer, right? So 10 ml of acetic acid, 10 ml of sodium acetate. Well, I got that one. Now, if I want to add exactly the same amount of acid that I added. So what I'm saying is 0.07 molar solution. If I want to prepare it in this one, how much NaOH should I be using? So again, we use M1V1 M2V2 formula, guys. Do we know what I need on this side? Yes, I need 0.07 molar. Do we know the volume of this container? Yes, it is 100 ml. Do we know the concentration of stock solution? Yes, that's 1 molar. Do we know how much we should be taking? V2, that's unknown. If we solve this one, can you tell me what you get here? What should be V2?
7 milliliters.
7 milliliters. Very good. So we got V2. If I take 7 milliliters, that would be same thing as adding 0.07 molar HCl into the buffer. Now we are adding 0.07 molar base into the buffer and see the change. Now, keep in mind, I'll just write down here, we went from 4.76 to 4.02. Look at the change in pH, because I'm going to ask you to do that. Now I'm going to add 7 ml of this solution, the stock solution. Let me clear up this. 7 milliliters, I added that. How much water should I be adding? See, I have 27 milliliters. I need to make the volume all the way to 100. How much water should I be adding?
73.
73. Okay, I added 73. Good. So look at the pH, guys. 5.51. So there was a change in pH, right? But now this went from 4.78 to 5.51. That's what you can see over here. That was a change in pH. When we added acid, it went from 4.78 to 4.02. Can you find me the change in pH for the first one and find me the change in pH for the second one? So when you're trying to find the change, just use the bigger number minus the smaller number. Can you find me that change?
Professor, wasn't it 4.76?
Yes. I think we were using 4.78 all the time. Yeah, you can use 4.76, but then use 4.76 for both of them then. If you're using 4.76, use it for both of them. Okay. Very good, Roberto. So 0.75 for the first one and 0.74 for the second one. It's roughly same. Why is it roughly same? Because you use the same concentration. So when you added 0.07 molar of acid, the pH dropped down by 0.74. When you added 0.07 molar base, pH increased by 0.75. See, that appears to be really close. In fact, they are the same, right? So this is the essence of buffer solution. You can go on either side, but at a certain point, you're going to run out of the mixture. So because, see, in this case, why was buffer solution so efficient? Because you had equal amount of HA and A minus. At a certain point, you keep on adding acid into the solution and A minus will keep on going down. At a certain point, that will be gone. When that is gone, you are only getting HA in the solution. And now if you add strong acid to this, pH is going to rise drastically, as you saw when you added acid into the neutral solution. You're going to see not increase, the pH is going to decrease. Hydronium ion will increase drastically when you add excess of acid. So there is a limit to which you can add acid or base into the buffer. And that we call it as buffer capacity. Every solution, every buffer solution has its own limitations, right? But then the best buffer is the one where HA concentration and A minus are exactly equal. Now, how will Henderson equation look like at that concentration? Let's look at that. We know pH equals to pKa plus log of A minus over HA. Now, for the best buffer, as I said, A minus and HA should be equal. So if they are equal, that's going to be log of 1, that's going to be 0, right? Let me show you in terms of equation. So I'll just take out this whole thing from here so I can write it down for you. Okay. So when HA equals to A minus, and if I simply plug in those numbers, this equation into the Henderson equation, I can simply say A minus over A minus. Why? Because HA is equals to A minus. So this is going to cancel out. And I forgot to put log. And log of 1 is 0. So pH equals to pKa. So the best buffer is the one where pH of that solution is equals to the pKa of undissociated acid. This is the best buffer because it has equal amount of HA and A minus. It's a perfect situation at that moment, right? Okay, now given that, let's jump on to another problem, which is quite similar to the buffers, but then not buffers, but the weak acids. This is about the solubility. So I will just clear up this thing. And guys, give me a second. I need to share my slide. Where is that? The one that we were doing. Well, where is that? Not sure why it's downloading it. That's strange. Shouldn't be doing that. Probably it's not. I'm not sure why they're doing that. That's strange. Okay, now it's completely, it's not responding. So it looks like it will take time. So what I will do is I will go back. I will just go back to the simulation until this thing actually, I'm not sure why it's doing that. I'll just go back to the simulation. Guys, all of you can see my simulation?
Yes, Professor.
Okay, so
Yeah.
here's what so here's what I'm going to do. I'm going to take out all this, and we will do, because I was planning to do this experiment at the end. Then that one is still not opening up. I'm not sure why is that. Okay, so the next thing that we are going to do is acid-base titration. Now, have you guys heard about acid-base titration before?
Yes.
Okay, now it is basically the means to know the concentration of your unknown acid or base. If you know the concentration of the known, you can go from there to the unknown. Now, what do I mean by that? Suppose if I have HCl reacting with NaOH, it gives you NaCl, which is salt, and water. Now, it's a very efficient reaction, right? Everything NaCl will react with NaOH. Now, suppose if I have 1 molar HCl, how many molar NaOH do I need to remove HCl from the solution? Completely remove HCl from the solution?
1 more as well.
1 mole, exactly, right? Because here you are looking at the stoichiometry. For every 1 mole, you need 1 mole of NaOH. So if you're using 1 molar solution of HCl, you need 1 molar equal amount of NaOH, right? So this is going to be 1 molar. And if you are using this as 100 milliliters, you need this one as 100 milliliters. Well, now suppose if you are given X amount of X moles, now this time I'm giving you moles. If you are given X moles of HCl, and when you start to react with NaOH, and it takes, suppose if it takes 0.19 moles of NaOH, can you tell me what this number is?
$0.19.
That's going to be 0.19, right? Because X need to be equal to the amount of NaOH, right? Okay. But now in a form of an equation, it works quite simple. This one essentially is your M1 V1 equals to M2 V2. Why is that? Because suppose if you multiply your molarity with the volume, what do you get? You get the number of moles. You multiply the molarity with the volume of the solution, you get the number of moles. And the number of moles should be exactly the same on both the sides, right? So you can find the amount of unknown if you know the volume of unknown, if you know the volume of known, and if you know the strength of known, right? Okay, now we are going to do one experiment on that. Let me clear this thing. So I'm going to take a strong acid. And let me see. So I'll just take that. No, I'm not going to take that one. Remove. Okay, so I'm going to take that. So I'll take 10 molar HCl. Okay. And Next I'm going to do is I'm going to take base. I'm going to use a strong base. Okay. Next thing I'm going to use, I need a flask. So I need one empty flask because I'm going to do that experiment. I need a volumetric flask as well. And then I go back to the stockroom. I need one Erlenmeyer flask in which I'm going to do this reaction. Okay, so right now, do you see the concentration of NaOH? It is 1 molar. What I need 1 molar HCl. Simple as that. I know I don't need 10 molar HCl. So I'm going to prepare 1 molar HCl. How do I do that? Using the same formula. I take, instead of 10, I take 10 milliliters of my 10 molar solution. And if I dilute it to 100 ml, this solution is 1 molar, right? Okay. Now, all of you can see, right? I'm going to put here 10 ml. Guys, do you see? I have 10 ml, 1 molar HCl solution in this flask. In this flask, right? This is 10 ml, 1 molar HCl solution. Okay. Now I'm going to put my base in this solution, right? How much base should I add to completely neutralize this solution? Now keep in mind, I have 10 ml, 1 molar HCl. How much base should I add into this so that all of my HCl is completely consumed in this reaction?
Professor, wouldn't it be still like 10 molar since you haven't diluted it yet?
No, I just did that. I just
Which-
did the dilution here. So
I
I
didn't see it. I'm sorry.
okay, I took a 10 ml, I added it here, and then I added water. And you can see the pH. pH is 0 because pH equals to negative log, and this is 1 molar solution, so it turns out to be 0. So that's what we have. Okay. So how much NaOH should I be adding into this solution?
10 milliliters.
10 milliliters, right? Because the strength is the same, right? So for 1 molar 10 ml HCl, you need 1 molar 10 ml NaOH, right? But then how would I know that the reaction is complete? Well, at that point, I'm going to use an indicator. And in this case, I'm going to use phenolphthalein as the indicator. Now, guys, keep in mind that indicators are weak acid, extremely weak acid, or they're weak bases. Now, at the end point, they are going to change their color. Now, phenolphthalein changes its color when you are dealing in a basic solution, not in acidic. It will change its color from colorless to pink in basic solution. So I'm going to add phenolphthalein. I will just add a small tiny drop. I will just add 0.01 milliliters, a tiny drop, right? We don't need to add more because if you add more, it's going to interfere with your reaction. Okay. Now, what I want you guys to do, just see what happens to the pH, right? Right now, pH is 0. At the equivalence point, when you have equal amount of acid and base, the pH is going to be 7. Why? Because the pH of water is 7. And at equivalence point, there is equal amount of acid, equal amount of base. They are going to react together to give you water and salt. The salt that you're going to generate is sodium chloride. Water is neutral. Sodium chloride is neutral. So your pH should be 7 at equivalence point, right? Now let's see what happens. Okay. Keep a tab on pH. Right now it's showing me the pH of NaOH. We are not looking at that. This is the pH of HCl. Okay. I will add 1 milliliter at a time. Do you see the change in pH? It went from 0 to 0.09. Do you see that over here, all of you?
Yes, Professor.
I'm going to add one more. So I'm adding base and the pH is increasing, which is supposed to increase. But look at the change in pH. I already added third milliliter, pH 0.27. Adding fourth milliliter, pH 0.37. Fifth milliliter, pH 0.5, roughly 0.5. See, you can check it over here, right? And it's an exothermic reaction. You can also see the increase in temperature, right? Okay, now I'm going to add my sixth milliliter. Well, I have already added 60% of NaOH and the change in pH is not much. Let's see what happens with the 7 milliliters. Not much. See, I'm expecting the change in pH to go from 0 to 7. And here, after adding 7 milliliters, I'm at 0.75. Not big difference. 8 milliliter. You can see it's 0.95. Ninth milliliter, 1.28. See, now when I add my last 1 milliliter, there will be a sharp increase in pH. See, right now I'm at 1.28, right? So what I'm going to do, I'm going to slow down. Instead of adding 1 milliliter, I'm going to add 0.2 milliliters aliquots. Let's see what happens with that. So 0.2. So I'm at 19.2 milliliters in my flask. I have added 9.2 milliliters so far. 9.4, you can see the change, 1.5. 9.6, 1.7 pH. 9.8, you see? Up till 9.8, we went from 0 to pH 2. And see what happens when I add my last 0.2 milliliter. That's the last one. See the change. It went from 2 to 7 directly. Now I have a neutral solution. Do you see any change in color in the solution? No, it is still colorless. Let me add another 0.2 milliliter, very tiny amount. Let's see what happens with that. Look at the change in pH. It went straight up to 12, right from 7 to 12. And do you see this one is slightly pink? Do you see? If you compare these two, you will be able to see the slight pink color. Do you see that?
Not really, Professor.
No? How about now? They don't look same, right? Well, that's where the science comes into picture and observation. Now what happens? If you are in the lab, first let me put 0.2 milliliter in to make sure that you guys can see the change in color. Do you see now? Still not?
Professor, it is visible, but it would have helped to have more kind of feeling.
Okay, now that's actually the point, because if you add a lot of that, so that's where you should be looking at. I mean, I added 0.6 milliliters above the equivalence point. Ideally, one drop, and you should be able to see it right there. A very, very tiny change. I mean, so you have to compare your colorless solution with the solution that you have. It should look like that, right? Okay, now, yes, if I add more, if I add simply more, and it's going to show up like this. You don't want this color, guys. Believe me, you don't want this color. Absolutely not. Right? If you show up this color, that means you have a lot of indicator which is interfering with your reaction, and you also have a lot of base that you have added. So the color should be really, really faint color. Okay, now here you saw two things. One was the endpoint where indicator changes its color. And the second one was equivalence point. What is the difference between that? Endpoint is where your acid concentration becomes equals to the base concentration, and everything is now neutral. It is at equivalence point. At the endpoint, you have slightly more of base, and that base is now reacting with the indicator, changing its color from colorless to pink. So endpoint is always slightly higher than the equivalence point, number one. Number second, what you just saw was the change in pH, right? So if I say change in pH and volume of NaOH that you added, the change in pH was not much, and then there was a rise, and there was a big sharp change that you saw. It went from 2 to all the way to 12 right away, right? And your endpoint, equivalence point, was in between, right? So guys, keep in mind, equivalence point is in between that sharp rise, number one. And where do you want your indicator to change its color? You want your indicator to change its color in this sharp region. You don't want it to change in the shallow regions. Why? Because the change in pH is not much. And if it starts to change color, you might be able to think, you may tend to think that you have already reached the endpoint, but your endpoint was right in the steep rise in the pH, or steep rise or steep decline. This is what you are shooting for, right? Now, if you take a weak base, a weak acid, then in that case, what happens? There will be change in pH, but then it's not going to be much. And then there will be a small region, and then it's going to be like, so this steep rise in case of weak base, a weak acid is going to be a very, very small steep rise. Why is that? Because when you keep on adding base, you know what happens? Your acetic acid, suppose if it is a weak acid, if it reacts with a base, what does it form? It forms sodium acetate and water. The moment you do that, you start to generate. So in your mixture, you have acetic acid and you have sodium acetate. What does this mixture tell you? You just prepare the buffer solution. And what do buffer do? They will try to resist the change in pH. Well, you keep on adding NaOH because you are generating the buffer in the solution. It will try to resist. So there will be no steep rise as you saw for the strong acid. For strong acid, it will go like this. For weak acid, there will be gradual rise, and then they're going to be rise in the pH, a short rise. And then again, it's going to be in a plateau region. So keep in mind, why do you see that plateau region, right? And why do you see that mild rise in weak acid? It's because you are generating a buffer solution. Okay, so having said that, This was about the titration of strong acid and a base, weak acid and a base, right? And you saw how indicators should change color. They should change color at the endpoint when you are adding slightly more of your titrant. Now, there are two terms I'm going to tell you. There's one term which is titrant, the second term which is analyte. What is analyte? Analyte is the one with an unknown concentration. Titrant is the one with a known concentration, right? So in your flask, you will have your unknown concentration. In your burette, you will have the known concentration, right? Analyte will be in your flask, burette will be in your titrant will be in your burette. So when you add your titrant into the burette, into the analyte in your flask, you will see that reaction, and at the endpoint, it's going to change color. Okay, that would be for the titration. Let me see what just happened with my slides. Well. Okay, it did open now. Finally, it did open. Okay, all of you can see what I'm seeing on my end?
We see the PowerPoint.
Yeah, you can see the PowerPoint. Good. So now suppose we are dealing with another equilibrium. Now this equilibrium, think in the sense of weak acid dissociation. First of all, I will write weak acid. Weak acid, you put it in water and it dissociates into ions, but not to that level, right? Most of them is undissociated. Now suppose you are taking a salt, right? Say, for example, sodium chloride. You put it in water. What happens? It completely dissociates into Na plus and Cl minus ions, right? Just like your strong acid completely dissociates into H plus and Cl minus ion, sodium chloride will do the same thing, right? But then there are some salts which will not do that. What are those salts? I will just give you one example. You take silver chloride, put it in water. Only tiny amount, so equilibrium is something like this. Only tiny amount will get converted into Ag plus and Cl minus. And this is an aqueous solution. This is aqueous. This is solid. Water is liquid. So only tiny amount will get converted into Ag plus and Cl minus ions. Just like you had weak acid, only tiny amount gets converted into the ions. In the same way, we have some salts which will get converted into the ions to a very, very small extent. These are not like these ones, NaCl, because NaCl is a strong electrolyte. So when we are thinking about the weak electrolytes, just like AgCl, tiny amount will get converted. Can we have this equilibrium in that form? Let me write it down for you. So suppose I take AgCl, solid. I put it in water. I write the equilibrium the way it is. And then I go for Ag plus and Cl minus. Now I can write the equilibrium constant as K, concentration of Ag plus Cl minus. And I'm going to write down in a different color so that you know what I'm trying to say. Tell me if this is correct. I wrote this in blue. There's a specific reason for that. Now, these blue brackets actually tell you, the square bracket tell you that your AgCl is dissolved in water. Is it really dissolved in water? Answer is no. So can I write this square bracket like this? Answer is no. Solid cannot be the part of equilibrium constant. That's right. So this cannot be there. So this is not the part of equilibrium. So I'm going to rewrite it one more time. So I'm going to skip AgCl. And now I'm going to put water into the picture. See, the way I wrote it for the Ka, I can do the same thing with this equilibrium, right? So I can write it here as K multiplied by water. That's going to be equals to Ag plus and Cl minus. Now, water is present in a huge amount, right? So what I'm going to do, I'm going to take this as constant because amount of water is not changing, practically not changing. So that's constant multiplied by equilibrium constant is a constant. So that would be Ksp, Ag plus and Cl minus. Now this one is your solubility product, which is given by Ksp. Your Ksp is your solubility product because it tells you how many ions are there in the solution. Now, if I simply write down that equation, okay, suppose I start with certain amount of my compound. Suppose I start with 5 moles of AgCl, right? How much Ag plus is there initially? There is no Ag plus or Cl minus. Do we have AgCl in the solution? Answer is no, it's not there. But now at equilibrium, so I will say initial change equilibrium. At equilibrium, suppose if I have X, this one is also X, the change in is plus X. Can I write negative X over here? Answer is no, because AgCl is not in the solution. I cannot write it over there. There is no such thing as negative X over here because that's not the part of equilibrium. So I can simply say Ksp equals to the amount of X multiplied by the amount of X. So I can simply say Ksp for the salts like these is X squared. In other words, if I know Ksp, I can find the concentration of ions in the solution. How will that work like? Square root of Ksp. So guys, we will stop here for the day. We will complete this chapter and start with thermodynamics in the next class. And one short announcement. All of you are here? Can hear me, right?
Yeah.
Okay, so I'm going to open the exam number 3 on Thursday once we complete this chapter, and that will be available to you until that's going to be there until next Thursday. And your exam 4 will be only on chemical thermodynamics, number 1, and for electrochemistry, you will be graded only based on the video quiz. So electrochemistry based on the video quiz only. So just to let you know, electrochemistry will not appear in your final exam. And it will not appear in your exam number 4. But then you need to do that. You need to complete the video quiz for electrochemistry, right? So that would be the grade for electrochemistry. So next class, we'll be doing this chapter. We'll be completing this chapter. We'll be starting with the thermodynamics, and we will go all the way to next Thursday when I'm going to open your exam number 4, and that will be due the before the final exam. Just to let you know, that's going to be due before the final exam. I'm going to give you the deadline for that one. It's one chapter before the final exam. Let me know if you guys have any questions. Otherwise, I need to rush for my next class.
Professor, I
We
I
have-
came I came 10 minutes late. Can you mark me present?
Yes, Leonardo, right?
Yeah.
Okay. I
What
just
about the
marked you present.
quizzes? So sorry. What about the quizzes for the last two chapters? So 16, I believe, and 17.
Oh, okay. I'm going to open that one as well. I'm going to open that one.
Thank you.
Mhm.